it's time to start the last session of this PADL. And this session has two talks. And the first speaker is Linda Brodo. The title of the talk is Dynamic Slicing of Reaction Systems Based on Assertions and Monitors. So please start.
Thank you. So I'm from University of Sassari, and this is a joint work with Moreno Falaschi from Siena and Roberto Bruni from Pisa. Okay, we start with presenting reaction systems, which are systems inspired by system biology, and was defined by Rosenberg and others in 2011. And we turn in the field of process algebra because we apply the structural operational semantics to reaction system in order to equip the reaction system with operational semantics and look at reaction system as processes. This is done in a previous work. And then the goal of this talk is to present the verification tool that we have defined, which is based on a slicing algorithm and that use assertion and monitors. Reaction systems are based on facilitation and inhibition. It means that we have a set of biological entities, and a reaction of a biological system is composed by a triple, and we have reactants, inhibitors, and products. And all these elements are sets, and that are subset of the set of entities, of, in a way, biological entities. Okay, so when we can execute a reaction can be executed taking a subset of entities, which is composed of your system. You can execute, you can say that your reaction is enabled if all the reactants are in the system and no one of the inhibitors are in the system. So the reaction is enabled and produces the products. So all the entities that are in the set P are available for the next computation. Otherwise, if you have not enough reactant or you have some inhibitors, the result of the computation is the empty set. So if you have a set of reaction and a set of entities, the result is the union of the product of all the enabled reaction. Okay. But when you execute a reaction system, you have an interactive process. In the interactive process, you have another component, which is the external context. This component simulates the work of the biologists that put in the biological soups some entities. So the execution of an interactive process is this one. At the beginning, you have the empty system, so no non-entities, and the external context provides you some entities. Then all the enabled reactions are executed and produce a set of products. And so all the enabled reactions are executed at each step. And their products are available in the next state. In the next state, the external component, the external context, can provide or not other entities. And so, again, all the reactions that are enabled are executed, and so on. Now, process algebra are abstract languages that are used to model distributed systems, and they are based on action and coaction. All the components in the system are independent, and they can communicate. The syntax, the very basic syntax of process algebra include the sequential operator, so a process can execute the mu action and then continue as P. We have also non-deterministic choice, so the computation can proceed as P or as Q. And then we have the parallel operator. Two processes execute their computation independently, and sometimes they can interact. And then we have the recursive process. When two processes that are independent can interact, if they execute an action, another can execute a coaction. Then, when this happens, the two processes can interact, and then they can evolve independently again. So, we borrow this idea of process algebra to equip reaction system with structural semantics. The structural semantics is used to define the semantics of process algebra with this rule. We have a rule for each operator. In this case, we have a transition. This process can execute mu, and then we have a label of the transition that records the action that has been performed. Here we have the two rules for the non-deterministic choice. So in this case, the P process has been chosen, and then all the process proceeds as P prime. In the other case, the Q has been chosen. And here is the rule for the communication where we have two processes in parallel. Now, we want to look at reaction system as processes. So each reaction is a process, each entity in the system is a process, and the context as well is a process. And we put all these elements in parallel, and we have what we have called at the beginning as the mixture. So every reaction, the context, and every entity are processes. It means that we have to define with the structural semantics their behavior. So we start with the external context, and we have that the context can perform the action that is provided to the system a set of entities. So we use the sequential operator, the action prefix. The context can behave in a non-deterministic choice, and this is a big difference with the context of the reaction system that was deterministic. And then the context can have a recursive behavior. So this is the definition of the behavior of the context. Here there are some examples of what we can express as the behavior of the context, and so we can have also, of course, a more complicated way of recursive definition. Okay, now we have the entities, and we can put all together, so we have only a set of entities in our system, in our process. Now, we have to define the behavior of the set of entities, and we have to define the behavior of each reaction. This is the behavior, the inference rule for the behavior of the set of entities. It means that if we have a set of entities, it will be a variable for the reaction to be executed. And we record this information in the transition label. And then we have no more these entities because they are consumed. As far as for the context can provide a set of entities. They will be a variable for the reaction to be executed, and then the context continues as Q. Here we have the two rules for the reaction when they are enabled, and then we apply the rule, we execute the rule, and we have as a result the product, the set of product produced by the reaction. In the case a reaction cannot be executed, we have only the reaction and no product are in the next state. So we have defined the behavior of each component of the reaction system in using the structural operational semantics. Here there is an example. Our system is composed of just one reaction, AB. This is the inhibitors, and this is the product. At the beginning, we have no entities, and then the context. The context can provide AB or ABC. If the context provides AB, and this is recorded here, then we can apply this rule, and then in the next state, we have the entity B. If the context provides ABC, okay, this rule cannot be executed, and the transition in the next state produce no entities. Okay. Now, this is fine, and the execution of a reaction system as process produce this. Very nice, but to understand something is not easy. So, for example, this is the execution of a model which more than 6,000 of reaction and 1,000 of context sequence. What we would to do is to say, okay, we want to put our attention on this entity, and we want to know which are the cause of these entities. Okay, for this, we need a verification tool, and we have applied the slicing algorithm. So the steps are 3. First, we generate a finite computation of reaction system, and it can be executed considering the context or can be context independent. Then we stop the computation, which is finite, and we select some of the entities. Who selects some of the entities? Maybe the biologists that are interested in those entities, or because there is something wrong, or because we want to know the causes, the reaction that have been applied to generate those entities. And then from that final state, the slicing algorithm performs a forward computation, eliminating all the reaction all the entities that are not necessary to produce that specific subset. So this is the graphical representation, and when we go back, of course, we select a subset of the reaction that have been applied and a subset of the entities that have been used. Okay, the slicing algorithm is simple, but it's useful. And also, we have applied other already existing slicing algorithm, and no one worked enough for our case. So this is a slicing algorithm specific for reaction systems. And okay, but now we could say, okay, the users say when the reaction system computation should stop. But now we want a method to automatically stop the computation. So we use monitors defined by Luca Aceto, and monitors are processes that are executed in parallel with your program and check if your program executed in a good way, otherwise stops your program. But what does it mean that your program executed in the right way? We introduce in the monitors some assertion. So we define some assertion, and we say that if your program, the reaction system computation, execute a step with label L, the monitors want that the transitions label satisfy the property F, and this is written like this, so the label satisfies the assertion, so your execution continues, proceeds, otherwise stops. And this is the syntax of the monitor. So when the monitor reaches no, the action no, the computation stops. And here you have no more action, but assertion. So you don't have the assertion that your process must satisfy. And then the monitor can have a non-deterministic operator, and also of course, the parallel operator, and also the recursive operator. Now, the assertion language. Our assertion language describes properties that our label should satisfy. Our label a little bit complicated, but all is composed always by set of entities. This is the entities produced by the reaction in the previous step. This is the set of entities provided by the context, and this is the set of entities of the reaction that have been applied or not. Now, what we can say with our assertion language, true, okay, or a subset of entities is a subset of some of these sets, or if one of these sets is empty. So what we can say, has the reaction A, B, C, B been applied? So are a specific reaction been applied? Or, for example, has the entity B played both as reactant or product? And then here there is the translation in our assertion language. But now we want to specify that the computation should continue if the transition label satisfies an assertion and stops as soon as a violation is detected. To do that, we rely on the safe recursive fragment of the NC-Miller logic. And why? Because we have a direct translation in the corresponding monitor. So we use the assertion language to specify a set of assertions. We use the NC-Miller logic to specify how the computation should behave considering those assertions, and then we have direct translation in the corresponding monitor. Now, we can have the execution of our reaction system in a way guided by the monitors. So if the label satisfies the assertion, that particular assertion, the computation goes on. Otherwise, when the monitor reaches the action no, the computation stops. And in this case, the computation stops at the state P3. From there, the slicing algorithm starts pruning all the reaction, all the entities that are not necessary for the production of a subset of element in P3. Okay, all this stuff have been implemented in this Prolog, and the name is BioResolve. It can be downloaded. So this is the structure of our tool. We have the reaction system syntax equipped with the structural operational semantics, and we also equip it with the structural operational semantic with some extension. Extension considering delay and duration of reaction, and equipped with some abstract quantitative information. Then we have a graphical representation, and then we can apply the slicing algorithm. Some example, here we have a metabolic pathway. Here we have a subset of reaction. And what we have done, two different computations. Okay, we have the same set of reaction, But here we have two different behavior of the context. In the first case, the context first provide the element in green and then the element in red, and we have this kind of computation. But if the context, the external context, provide first the red entities and then the green one, we have another complete different, almost, computation. Here is the result of the slicing algorithm that is stopped, and the slicing algorithm has been applied as soon as in the state where for the first time the entity's mitosis appears. And here is the sliced context. So we have the computation, so the monitor stopped the computation as soon as in the system appeared the entity mitosis. And so this is the backward computation. So these are all the entities necessary to produce the mitosis. Here are another two examples. We have here 33 reaction and context-free. And for computing 6 slicing steps, the tool takes 9 milliseconds. Here we have a model with more than 6,000 reactions. It was the model we showed before, I showed before. And the time is 6,000 milliseconds. Of course, the performance is not at the moment our goal, because we are concentrated more on verification of properties. So conclusion, the slicer computes automatically a simplified computation. We can deal with computation with or without context, monitors to identify states which violates a property using an assertion language, an ad hoc assertion language, and we propose an implementation. So what we want to do in the future, of course, add forward slicing and not only backward, improve the interface, and apply the slicer algorithm to the quantitative extension that considers speeds, delay, concentration levels. Thank you.
Okay, thank you very much. So questions?
The biological application remind me a little bit of Walter Fontana and other people's work on the Kappa language. Are you familiar with that? And do you know about the Kappa modeling language?
Kappa? No.
Okay, so for chemical reactions, it reminds me of this to some extent, but I don't think they have the monitors. It might be something worth looking at. I'm curious if some of these techniques could be applied to Kappa.
Okay. I will check for the Kappa. Well, we only consider the example, the example in the KEGS database.
The Kyoto, the KEG database?
The KEG.
KEGG?
Yeah, database, but it's hard for us to translate that model in our model because many information are missing for us. Yeah, that's the problem.
Thank you.
Other questions? So then I ask you a small question. So I'm not so familiar with that example, but so the number of reactions, the practical, or so this example is simplified one from the real example, or so.
Sorry?
So I guess there are many reactions or loops.
These are reactions. Of course, it is a big simplification, because the reaction system are qualitative methods. And using the structure operational semantics, we improve by introduct speed and delay and concentration levels, but of course in an abstract way.
For real examples, you need more example. What the current one is the number of the reaction. Current number of reaction is usual.
Yes. For this example, we found this example. Where is this one? This example was initially modeled using Boolean networks, and we translated from Boolean networks to reaction system. Okay, it was easy because from Boolean network to reaction system, it's easy to translate.
It's automatic or by hand?
No. Unfortunately, no. But this is the same question. And biology, bioinformatics told me, if you find an automatic or semi-automatic way to translate a model of biological system into this language, you win. But it's like the Santo Graal, something like that, to have a language in between biologists and computer scientists. It's not easy.
Thank you.
I'm just looking for a parallel to what happens inside many sequential neural networks, and wonder if there's any kind of connection or possible similarities between these processes and neurons.
So neural network?
Yes, because there we can have kind of high-dimensional vector describing the state of the context in a way. And then in that case, the network works very deterministically, computing as a function the next layer, but activations. But here it is more like you have free choice or this kind of disjunctions there. But still, do you see any connections?
It's hard to say. We for example, we try to. But you mean neural network, computer science, neural network? No, we didn't see about that. But we try to translate the communication, to model the communication between two neural cells. And in that case, we discovered that it's important to consider membranes. And we are working on that. We are actually working on that, but no connection with computer science neural network. I mean, until now.
Okay, other questions?
Could you use these techniques for DNA strand displacement?
No.
No?
No.
Okay.
No, it's all.
It's too different?
Yeah.
Okay.
Too different.
All right, thank you.
Other questions? No? Then let's thank again.
Thank you.